Okay. So may I start the second tutorial? Sure, no problem. Yeah, so I'd like to start tutorial number 2. Yesterday I heard Professor Khan gave some tutorial lecture of the parameter or the how to read the Smith chart, etc. And this is my turn, and I prepare some tutorial of the examination for students, mainly on the topic of the first day and the first lecture, Maxwell's equation, Friis transmission formula, and impedance matching of the Smith chart. So I hope you have some paper. If possible, we need some calculator or the Excel on PC or etc. But maybe if you don't have any Excel or the calculator, please check line by line. I will explain the calculation method on the Friis transmission formula and Maxwell's equation. So let's start this tutorial. So this is a tutorial or examination number 1. So first of all, I explain this Maxwell's equation. And mainly, we use this to Maxwell's equation. And answer the question about the Maxwell's equation in condition that medium is isotropic and uniform. This condition is very important. And so derive the general solution for the electric field EZ by Maxwell equations in condition that the electromagnetic field has E j omega t as a time factor and propagate in the direction. And where E0 is amplifier of the electric field, and R and omega are the position vector and angular frequency, respectively. And of course, J is an imaginary unit. And it's possible to use the vector formula, this one, etc. So, can you solve it? Please try. This is a tutorial. So please try to solve or transform this Maxwell's equation. Once I explained at the first day and the first lecture briefly, but now you can solve by yourself. Please try. So it's very difficult. It's a very basic question or basic examination for the electric department in Japan. So I'd like to introduce the transformation in order. Please check it. So, of course, this is an assumption in this case. On the examination, on the condition, we consider E vector is E and E j omega t minus j omega z. And the other element of the H, D, D, additionally J, can be described this formula. This is a very basic assumption, first of all. And from here, we can solve this very complex formula, especially this dt dv or dt dv. So this Maxwell's equation number 1 and number 2, please put these parameters here. As a result, rotation h is still rotation h, for example, in this case. And this right term can be changed to this formula because it involves j is equal to here and dt 分の dt. So it's converted to j omega epsilon e here. This is a term of t time. So we can change, we can transform this term to j omega epsilon e. And now we neglect the j omega z term. So it's the same. Rotation h is the same. dt 分の dv. So the b is here, and so this is term of h. So you can change this form to j omega. So j mu is here, and omega j omega is here, and here it moved to here, and j omega mu h. So now it's very simple equation, except rotation. So next we need to transform this rotation of vector equation. So now we have these two equations from the Maxwell's equation number 1 and number 2. Here you can see the same h or same e. And now current problem is to solve the E electric field. So here you can see the h, and please put we multiply rotation again in this left formula. So rotation E is a left term. And this right term becomes a rotation minus j omega mu h, and rotation h is equal to omega j sigma plus j omega epsilon e. So finally, we get only the E formula here. Double rotation E is equal to j omega mu and sigma plus j omega epsilon E. We can solve it because there is no other parameters. Only E parameter of E is in formula. And next, in this problem here, this is a vector formula, very basic vector formula. I suppose you've already remembered. And when we apply this rotation E is equal to etc., we can transform. We can transform this left term based on this formula. So this rotation H is equal to gradient divergence E minus sigma 지조 E etc. And now in free space and uniform space, we can assume divergence D is equal to 0. Divergence D is equal to 0 is here. Free space, there is no value here, is equal to 0 in free space. So through this transformation by the vector formula, we got this double rotation H is equal to minus sigma square E. And now right term is the same. So compared to the previous double rotation E, this is very simple formula, only with E, electric field. So we write it very clearly. This is a result of the transformation by help of the vector formula, etc. And so we change this formula in one side. For example, we move this left term to the right term, and we get this formula. And this is a very complex number, so we assume this minus j omega mu and sigma plus j omega epsilon is equal to k square. And at last, we get this formula. This is named the wave equation. So this is a very basic formula related by the Maxwell's equation. So can you follow this transformation? And from this wave equation, we got a general solution here. It's a very simple simple solution from this simple equation to this answer. And from here, so we get the EX, electric field is described as a wave when the T changes and phase of this electric field rotating by help of Ej omega T. And additionally, in Z direction, it's the same, Ejkz plus time is only one way, but Z position is a three-dimensional way. So in this case, positive propagation and negative propagation, we must combine. So as a result, this formula we get from the Maxwell's equation. And we can write this formula on the figure here. Now here is E components only, electric field components only. And additionally, we can solve the same way to the magnetic field. And as a result, we can get E field is propagating by time and by position, like this red wave. And in particular, magnetic field propagate in this particular propagation. So this relationship between this electric field and magnetic field is fixed. So there is no conversion. Now we put electric field here. Magnetic field is vertically on the left side. And next, this is a sinusoidal wave. So this wave changes so by time and by position, but the relationship between this electric field and magnetic field is fixed. So this is the waveform. Usually waveform of the radio waves. So when we stop the time and we check this waveform in space, we can see this change of the phase and amplitude in space. And when we stop, we fix the position. For example, in space, this wave is fluctuates in time. So this radiation, wave radiation, propagate by change in time and in space, both. So this is a solution of the wave equation. Please remember it. this is a very basic examination in Japan and maybe in the world, transformation from the Maxwell education. And if we got this solution of the wave equation, next, this is a tutorial B, and so it's an examination. So derive characteristic impedance for the free space propagation. And I need a number itself, not character, not parameters. It's easy to calculate the number itself for in free space propagation. Hint is I suppose in the first lecture I explained briefly characteristic impedance is a ratio of the transverse components of the electric field and the magnetic field. It's additional information in case of a TM mode. So first of all, we got this solution of the E and H, and we have the other relationship in the Maxwell equation here and there. And finally, so I suppose now you are wondering what is happening in my talk. So this is a answer of this tutorial B. So this is a ratio of the transverse components of the electric field and magnetic field in TEM mode. So H and E, we calculate, we estimate the ratio of H and E. And as a result, this component of the magnetic field and the electric field is transformed to the omega mu over K in this case. And K is defined as I mentioned before here. K is here, so we put K, and this is omega mu, and square is here. So this is a wave propagation, first of all. And here you can see sigma, epsilon, mu, omega, etc. And I give you the condition of the free space. So if we assume free space, this sigma is equal to 0 because it's a free space. So this equation can be changed to this formula. And additionally, epsilon and mu is equal to epsilon 0 and epsilon mu. It's a parameter in vacuum or free space. And now you check the real number of epsilon 0 and mu 0, and as a result, this impedance becomes 120 pi. This is a very basic number of the impedance of the free space. Can you understand it? And this question involved here. So now I assume epsilon 0 and mu 0. But if wave propagates in the other dielectric media or the other media, so number of epsilon or mu is different. Impedance changes. And I will explain in next tutorial speed of the propagation changes. So at last, if the wave propagates in different media, different epsilon or different mu media, reflection or refraction occurs. So this is a first parameter to describe the characteristics of the radio wave generally. So please remember, impedance in free space is 120 pi. And next, we can derive the velocity of the radio wave for free space propagation. Maybe you need support. So this is our answer of the velocity. And the velocity can describe of the omega over beta. So velocity defined to the ratio of the omega and beta. So time change of the radio wave and propagation. So from this equation, this relation, we put these parameters instead of beta. And here you can see the same omega, and now omega has gone anywhere. It means velocity of the radio wave is always equal to root mu epsilon. So 1 over root epsilon mu. There is no parameter of the frequency. It means from the 50 hertz as electricity, microwave 2 gigahertz, for example, or terahertz wave, or optical wave, for example, petahertz or other speed is the same. And if we can assume this epsilon is equal to epsilon 0 and epsilon mu, mu 0 in free space, this velocity can be changed to 1 over root mu 0 epsilon 0, and it's equal to light speed. So in this course, maybe mainly at the first day, I explain you Maxwell's equation can describe all electromagnetic wave. It involves electricity, very, very low frequency, microwave, the radio wave, or light, or visible light, ultraviolet, X-ray, etc. So here, light speed is not only applies the light optical propagation. Even in the radio wave, or even in the electricity, if this very, very low frequency electricity can be transmitted to free space. Of course, in this case, we need a very huge antenna. But light speed is not related with sigma. So all phenomena, radio wave propagation is with light speed. Not only in the light, but also in the radio wave or electricity itself. It's very important. And additionally, this is a result I put the mu 0 and epsilon 0 because we assume the free space. So please go back to the original one. If media in propagation changes, or the other media speed is changed, not light speed, a very slow speed will be. So impedance changes and speed changes in different media. So go back to Snell's law. So if wave propagates into the different media, different means different epsilon or different mu or different impedance. And but Maxwell equation is perfect, as I explain again and again. So even if so in different media, propagation speed is different or impedance is different, but there is no special point when we solve the Maxwell's equation. So to satisfy all the Maxwell's equation in all area, unfortunately or fortunately, this wave refract to this line, and part of the wave reflect to satisfy the back solicitation. So this is the meaning of Snell's law. And in second part of today's tutorial, I'll give you the equivalent circuit model. And so sometimes today or yesterday,